let us see the simulation for the Hartley oscillator. I hope you are comfortable with doing the connections for the any kind of circuit. So that's why I'm not going to do the connections. So directly I will place my circuit diagram as it is. I have done the connections before, and the design part, let us see once. This is where I keep a CE amplifier, the same CE amplifier which we have simulated in the previous classes, and which frequently we were using. The same circuit is connected, and as we know, the circuit which gives like a 180 degrees phase shift. So in the beta network, in the feedback network, for sure I have to keep a similar kind of network which offers 180 again, because the circuit which we keep it over here should be offering the amount of the phase shift, so that the total phase shift should be around 360 degrees, so that it will be satisfying the condition of Barkhasen, right, criteria need to meet, so that the total circuit can generate oscillations. So on that purpose, I keep a CE amplifier over here, and the network which I connected to is expecting that 180 degrees phase shift. So that 180 degrees phase shift will be offered by the tank circuit by having some kind of mechanism where single inductor actually to be there, but it was split into the two components and connecting ground in between, so that phase splitting network will be forming over there, so that 180 degrees phase shift will be offered. So the entire circuit, what I assume that it will be giving a oscillations with the frequency of, we have derived that the frequency of oscillations that we generated across Hartley oscillator is 1 by 2 pi root LC. So L is nothing but the equivalent resistance of this one plus this one. So what I do is, so here I have a Excel sheet. So here we have Excel sheet. What I've done is just updated that all formulas, and only the thing I have to give the details of what kind of L and what kind of L2 I'm using, and what is the amount of the capacitor that I'm using. So if I do this, and what the formulas are giving is, here what I'm trying to do is, so let me show you how the formula is updated here. So this is the cell where I'm trying to update the value with the sum of the L1 value plus and the value of L2, so that if I give some value of L1 and L2, so automatically L equivalent, which is the sum of these two, will be updated. So for suppose L1 and L2, if I'm using at 1 millihenry, so 1 milli in the sense 1 into 1 into a power minus, like exponent 10 to the power of minus, that is the notation, 10 to the power of minus 3. So it's around 1 millihenry. The same value if I use it, same value if I use it here also. So totally like L1 plus L2 will be the value of 2, and if the value of the capacitance initially, let me use it, the value 10 into e power minus 6. So this is around 10 micro. So here the formula is mentioned like 1 by 2 pi. So you can see it over here, 1 by 2 pi, 1 by 2 pi under root square root of L1, L6 and M6. L6 is the location of L equivalent, we have it, C equivalent we have it. So L equivalent and C equivalent is multiplied over here, and the square root is calculated, and which is multiplied with 2 pi, and 1 upon of that one will be the calculated value which will be updated over here. As we know the formula, F is that one. So like that, if you drag this one, in all cases whatever the L value and C value we are using, you can see the updated value of the frequency. So it is easy that when we go with the multiple cases, using this kind of Excel sheet, where we can go with some kind of advanced analysis where we need not to spend much time in doing the calculations. So now I will be providing this Excel sheet in the description. You can download it and you can further continue the rest of the calculations. So here first case where I'm trying to keep the L value equal to 1 micro and milli, and L2 is also 1 milli. So let me take the same values over here in the circuit diagram. So L value is 1 milli and L2 also 1 milli, and keeping the capacitor over here, it is 10 micro. And this is my amplifier circuit across the output, where I can expect that oscillations are generated. So that same oscillations I can see it monitor across the oscilloscope, and the frequency of the oscillations I can see it through the probe, dedicated probe which I'm trying to connect it here. So let me show you how I keep a probe over here. This is the probe which I connect it. It will be showing the voltage reading itself, but what I do is I'll be going with the right click and I'll just change the properties where the appearance, the parameters where I have it, I will do the customize that. What customization is required is I just need the frequency of that signal which I need it, just I'll make it S and I'll give it OK, so that not only the voltage reading across the voltmeter, it will be showing the frequency of this one also. So now across the voltmeter I can see both the things. I can see the both the things. I can see the both the things, the voltage reading as well as the frequency of the oscillations which I get it across the output. Yes, so let me do the simulation. Yes, so this is how I will be getting oscillations. Yes, so where I started with the noise, where it started with the noise, so where across the channel A, which I connected a channel A only, I don't bother about the channel B. So if you connect like a channel B at input of your amplifier, you will be getting 180 degree phase shift. So I don't bother about the rest of the parameters. I just need whether the oscillations are generated or not. So if I zoom it, yes, this is how like oscillations are generated. And if I change the time scale, you can see that the actual oscillations which are generated across the output. So just I'll close this one and I can see that the frequency of oscillations across this one is around 1.12 kilohertz. So now the same thing like I'll update over here. So the RC which I'm connecting it across the amplifier is 2.2 kilo ohms, and for the values of which given a capacitor and inductor values, I could generate the frequency around how much 1.12 kilohertz. So it's around like the same value 1.12 kilohertz. Yes, 1.12 kilohertz. So which I have calculated through the formula. Theoretically it is around 1.13 into 10 to the power of 3. It is also 1.13 kilohertz. Means the theoretical calculations and the practical frequency that we got it across the oscillator both are same. And for the given tank circuit, we could generate oscillations. We need not to worry about like oscillations are started with a small strength, and if it is becoming a like a sustained one, like is that the sustained oscillations will be continued up to infinity or not? That's what the thing to be considered. So at t is equal to at in the steady state, we are generating a sustained oscillations. If you zoom it, and you can see that the actual oscillation with a particular period. So this is how like oscillation with the zero strength to the sustained oscillations are generated in the first case. So this is what actual oscillations which are required. But what I need is the frequency of the oscillations is 1.12, where I need like more than that frequency, where I want to do some modifications across the tank circuit. Is what I'm trying to do is I'll be doing the modification across the tank circuit. What I do is I'll just change the capacitance value. I reduce the capacitance value by 10 times. I reduce the capacitance value by 10 times. I'll redo to the simulation. The frequency which I got it around this much, but the problem is The problem is, if I see the oscillations over here, yes. So what happening is we can see that oscillations which I got the oscillation with the strength of this one, but it is getting decayed, so we call this one as decaying oscillations. So as I shown already, when the case we go with the inductor value is the same, both inductors we are keeping that as it is in all four cases which I am trying to show, that different possibilities, four possibilities. In all four possibilities I am keeping that inductor value same. So L1 plus L2 will be the same. What I'm trying to do, I'll be doing the adjustment for the capacitor. So here 10 micro, here what I'm trying to do, 1 into 10 to the power of minus 6, so it's like 1 micro. So I'm giving 1 micro, so here 10 micro, it is 1 micro. And the calculation of the frequency theoretically is around like a 3.56 kilohertz. So we need to get like 3.56 kilohertz, but we are not able to get a sustained oscillations. It's decaying oscillations. So the reason to get a decaying oscillations across the output is, so we can see that this is what the frequency of oscillations across the tank circuit, across the oscillator. And if you do the calculations, if you do that analysis once again, the calculation of A beta which we have done it is this one, uh, which we observed this one, where A beta value is calculated. Once you calculate the A beta, we got it like A beta is nothing but a gain of the amplifier A into the beta value is nothing but what kind of tank circuit we have connected. So we have connected a amplifier circuit along with the tank circuit over here. So Z3, Z1, Z3, Z1. Sorry, this is what Z1. So Z3, Z2, Z1. Z1 is hmm. So Z1, Z2, Z3. This is what our tank circuit. So Z1 is the inductor and Z2 is the inductor. Z3 is the capacitor. So now if you do the calculations like that, so finally we got that the gain will be this much. So A beta will be this much. So let me take a screenshot that A beta is this much. You put it here for suppose. Yes. So what we know is the A beta of the oscillator that decides, A beta of the oscillator that decides, A beta of the oscillator that decides the type of oscillations that it generates. A beta if it is, A beta if it is, A beta if it is 1, or A beta if it is less than 1, or A beta if it is greater than 1. So based on the value of A beta we calculate, if the value is very less than 1 or greater than 1 or equal to 1, we'll be getting different kind of oscillations. So here greater than 1 in the sense, it will be started with a very low strength and it will be becoming a strong. So increasing kind of oscillations you will be getting. Yes, this is the possibility when we get it this one. And in this case, less than 1 in the sense it will be started with some kind of strength, and the moment you increase the time, like next oscillation will be the less than the strength of the previous oscillation. This is how decaying oscillations will be coming into the picture. Yes, so this is how strong oscillations becoming zero oscillations, right? This is how decaying oscillations will be generated across the amplifier and the beta network, whence like a amplifier gain and beta gain will be less than 1. If it is 1, that it called a sustained oscillator, where it will be generating a sustained oscillations with the same strength. Whatever the strength of the previous oscillation, that will be the same strength of the next oscillations also. So it will be generating a constant strength. So as we need, as you see that A beta greater than 1 or less than 1 and equal to 1, so where we can generate a different oscillations based on that. But here what happening is, in the first case we able to see that sustained oscillations are there. There the oscillations of this one will be the same strength of the next oscillation also. So it will be having the same strength forever up to infinity. So every free oscillator will be the same strength with the next oscillation. So right, we call this one as a sustained oscillation, where we have that a beta equal to 1 for sure, right? But when we are going with the first case to the second case, where in the first case we are keeping 10 microfarad, here in the second case we are keeping 1 micro as a faraday, 1 microfarad as a capacitor. So where we are going with different cases, we are going with different cases, we are going with the different cases, we are going with the different cases. I'm trying to keep like a L value 1 and L2 value both are constant in every case. And what I'm trying to do, the C value I'm trying to reduce, C value I'm trying to reduce. So first initially I took like C value is around 10 micro. I'm keeping a C value 10 micro. In the second time, like I will be keeping a C value 1 micro. In the third case, I will be keeping 0.5 micro and a 0.3 micro and a 0.2 micro. Like that, I will be reducing the C value every time. So as the C value is reduced, C value is reduced. So here, as I say, X1 is a inductance reactance and X3 is the reactance of the capacitor. Yes, it is nothing but a 1 by j omega c. As the c value reduces, as the c value reduces, this term will be reduced, so the x3 value will be increased. So x3 value is increased in the sense, this value is increased in the sense, the old term, old term the old term, this old term, right, x3 value increases, so this old term decreases. So that a beta which you mentioned it over here, the beta value is reduced, so the a beta value is reduced, so it will be going with this case, it will be going with this case. So this case is now we got it because of the value of x3 is increased, because of the x3 value is increased, so this time is decreased, so that a beta value is reduced. So now because of this one, we know we got this kind of oscillation, this kind of oscillations, a beta is reduced, a beta becoming less than 1, right? So that we will be getting a decaying oscillations, right? Every time it is trying to sustain some kind of strength, but it is becoming a decaying oscillation, right? So the strength of the oscillation becoming zero, so strength of the oscillation becoming zero, strength of the oscillation becoming zero, it is nothing but a decaying oscillations because of a beta is less than 1, right? So now what is the solution, right, to get a decaying oscillations into the sustained oscillations is, whatever the a beta which we have it less than 1, we have to make like a beta greater than equal to 1. So for that, whatever the strength the beta value is reduced, we'll be trying to increase the a value. So a beta is the strength which is reduced by increasing the gain of the amplifier. Now I have a solution that I increase the gain of the amplifier now, so that I will be compensating the problem with increasing the a, so that a beta becoming 1. So a beta becoming 1. So now only the thing we have is we have to increase the gain of the amplifier. So in the simulation or in the doing the hardware, in both cases what we do is, so here we have to do the adjustments, variable capacitor which you take it, along with the variable resistance also we have to take it, and we have to do the analysis, we have to do the experiment. So variable resistance in the sense, whatever the resistance we got it, it's around 2.2, we kept it 2.2, we keep it around 2.3 kilo ohms now. So that what happening, that as we know, pull up resistance is increased, so that automatically the gain of the amplifier will be increased, so that overall gain a times of beta it might be increased, so that you will generate a sustained oscillations which is like a decaying oscillations. Now we can get it as a sustained oscillations. We'll try that case, Now what I'm trying to do, so where I'm not unable to get a faithful oscillations across the oscillator, so the solution what I do is I have to make the resistance value high. I have to make the resistance value high 3.3 kilo ohms, so that the resistance value is becoming high, gain of that amplifier is becoming high, A beta will be becoming high, so that it may get a oscillation, sustained oscillations across the output. Let us do the simulation once again. So now if you see, so previously it was decaying, so it is trying to get a oscillations with some strength, and it is trying to maintain the same strength. It is trying to maintain the same strength. It's not getting decay at any moment. Yes, so it is generating a sustained oscillations. If you wanted to see that the actual oscillation with the some period, we have to change the scale. So if you change the scale, you can see the actual oscillation across this one. And if the oscillations are generated, if the circuit is generating a proper oscillations, we have to monitor what will be the frequency of oscillation that generates. So here we can see 3.53. This is what theoretically we have calculated through the Excel sheet. The updated value we got it around 3.56, and which we expect 3.56. Previously 1 kilo is around, now it is around 3.5 kilohertz. So increase the value of the frequency. Alright, where I need that maximum gain amplifier. So previously this is the amplifier which can generate this frequency, where I need like maximum frequency. Right, I couldn't generate the same amplifier. With the same amplifier, I can increase the amplifier gain, so that I can generate the frequency of this one. Yes, so now I will be going with the third case. What I do is I need that more than that frequency 1 kilohertz to the 3.5. I need around 5.4 kilohertz. For that what I do is I will be keeping the capacitance over here. It's not 1 micro. I will be keeping 0.5 micro. 0.5 into 10 to the power of minus 6. 0.5 microfarad, that I'll be keeping. And with that it is giving like a 5.4 kilohertz frequency. It is giving 5.4 kilohertz frequency. So that is the frequency that I expect by keeping the small capacitance than the previous one. So because of that, what happening again, like what happening, the C value which we got it previously, which we kept it previously, the C value which we keep it in the previous case, then that will be reduced the C value, so that the XC value will be increased further. So XC value is increased in the sense, X3 value is increased in the sense, this value will be increased, that overall beta value is decreased. So that A beta again it will be reduced, so again you may get a sustained decaying oscillations. So let us see, are you getting the decaying oscillations once again in the simulation? Right, what happening in the third case, I'm trying to keep the C value not even that much, 1 micro. I will be keeping that 0.5 micro. So I'll just observe that across the output. All right, across the output, yes, again the same problem, we will be getting a decaying oscillations again. We can see that in the third case again, in the third case again, in the third case again, when I go with the when I go with the that capacitance over here is 0.5 micro, like a very small capacitance. Because of this one, that capacitance value is reduced in the sense reactance will be more, so it will be offering more impedance, so that the attenuated signal, like the attenuation will be happening more. So it is attenuating more in the sense the attenuated signal will be amplified with the maximum strength of the amplifier. So for that 3.3 is not enough, I need more than that. Yes, so when I keep 3.3 itself, that amplifier gain is not enough for us to generate a sustained oscillations. So what I need to do is, this is how I got a oscillations with the small capacitance. What I have to do, I have to make sure to get a sustained oscillations from this case to this case. When you keep this much capacitance, you have to increase the A value. So this is what the resistance which you keep it for getting that oscillations of faithful from this one to this one. Now what I do is the 3.3 kilo ohms, now I made it as a more than that. Yes, I will be keeping 4.4 kilo ohms now. I'll just check. So is that any decaying oscillations will come at any time? No, it's like at any time you are not getting any decaying oscillations. Just observe that it will be continue with the same strength of the oscillations. Next oscillation will be the same strength of the previous. So that is how like a sustained oscillations are generated. So you wanted to see that the frequency of like you can see that the oscillations are visible across this with the same strength of the previous oscillation. That is how the sustained oscillations are generated. So I don't have any problem with the oscillations. So this amplifier with the small capacitance which we expect like maximum frequency that can be generated by this much strong amplifier, so that it will be generating 4.97 kilohertz. 4.97 kilohertz, it's around 5 kilohertz. So whatever the theoretically we expect that amplifier, we expect the frequency, we got it the same frequency here also. Yes. So like that we continue with the rest of the cases also, where you need like maximum frequency, whereby reducing the capacitance value, the compensation should be done by increasing the gain of the amplifier. So like that we can continue for the rest of the cases. uh, at any moment if you get this kind of decaying oscillations, you feel that oscillations are wrong, you have to make it correct by changing the amplifier gain. So that is the purpose why we keep the variable resistance across the RC and a variable capacitance. You adjust this one, parallelly you adjust this one also, so that you take a readings for different oscillations, different frequencies across the output.